All right, guys, so let's get started. The topic for today's lecture is diffusion of innovation. Oh, by the way, can you please lower a little bit the lead of the computer so I can see the room a little bit better? Наклоните его чуть-чуть. Yeah, perfect. All right, perfect. Thank you. Okay, so the topic for today's lecture is diffusion of innovation. And we're going to sort of continue and build up on the topic of information propagation we worked on last time. And, discover sort of new models. And I hope I can make this work. All right, so we're going to talk about diffusion of innovation, just sort of the big picture, the general idea. Then we'll look into very particular influence propagation models. And then we'll set up a problem of influence maximization. I will explain how algorithm works, the one that finds, helps to find the maximum influence. But again, we're not going to go deep into the details of the algorithms. So, okay, let's get started. First of all, I want to kind of outline and differentiate what we're going to be talking today from what we did last time. So last time we talked about this sort of information or sort of disease spreading based models. And it is about that those models were dedicated to calculation, the propagation of maybe viruses or infection, rumors or news. You can also think about ideas. But the key message there, one of the key properties in that model was that from a receiving person, from the receiving part, for the person who actually receives information, there is really no decision needed to be made, right? So, you're in a contact in the same room with somebody who has a flu. Well, there is a chance you're going to get a flu. And, flu doesn't ask you whether you want to get sick or not, right? Or, when the rumor spreads around, again, somebody comes and tells you some news, there is nothing required from you when you're receiving those news. Eventually you just know it or not. You can actually spread it further or not. But in terms of your knowledge, you're getting the news, you're being told that you heard it. You might want to unhear it, but well. Anyway, so that's the story with information. When we're making decisions, situation can be slightly different. Let's say you're making decisions, to buy a house. Okay, well, let's say you're making decisions to buy an iPhone, not to buy an iPhone. Well, there is your opinion about it, of course. You might look, on the internet and see what the properties are, the pricing, etc., etc. But you also quite often will look at your friends, right? And sometimes whatever your friends do does have influence on you. And depending on the people, of course, you're much more influenced by your friends or less influenced by your friends. Another example of decision making is like, let's say if you're considering joining political protest, right? One thing to go there alone, another thing if your friends going out there. And if one of your friends goes out there, it's one story. But if 9 of 10 of your friends, like 90% of your friends joining this movement, there's a very good chance that you will join too, right? So those decisions, joining political process, protest, purchase decision, or even decision of switching to a new technology can be very much dictated by, your friends or people you work with. I'll give you another example. Some of you are on the Mac, some of you on PC now. Let's say, there are different opinions, but let's say you're considering switching to Mac. You realize that it will be much easier for you to switch to Mac and to work on Mac if people who you know and who you communicate with are also on Macs, right? The same operating system, you can exchange knowledge, maybe some programs. So your selection of technology can be influenced by people you work with or you communicate to, right? Again, if you actually work somewhere in your office is on PC, try to bring their Mac. You will realize it's incompatible to a lot of processes within the office. So when you have to make a decision, you actually, look around and look at the people you work with. You look at your friends and you compare your choice to their choices. And surprisingly, this sort of local behavior actually causes very significant can cause very significant changes in a global picture. So it's sort of one of those things when microscopic changes, lead to macroscopic results, and sometimes quite unpredictable, as we have seen with, Arab Springs, for example. This notion of diffusion of innovation is actually goes back many years, and one of the famous studies on this sort of separation of information propagation in actually decision making goes back to like 1940s longitudinal study done by Ryan and Gross and in the States, and the study was about adoption by farmers of a hybrid seed corn. Okay, so the story is very simple. There was one type of corn that farmers had been using for a long time. Then a new type of corn has been introduced to the market. So-called hybrid corn, and it was producing much more than the previous one, but it took a long time for farmers to start using it. And the study actually is longitudinal through many years. And what's interesting is if you look at the screen, you will see two histograms. So the first one, this white histogram, it actually shows right here, right? Like this histogram, right? It actually shows you the number of people, the percentile of people, of farmers, who heard about the corn. So they heard about it, but they kept using the old one, right? And then the other histogram is actually giving you the histogram, the distribution of farmers who started using it. And notice that they're both like normal distribution, but one is shifted with respect to another by at least 8, well, probably what it is, 7 years, right? So has been a delay in adoption. So people heard about it, but has not adopted. And from these curves, if I, for example, this is really just the number of people who adopted per year, right? And the question is sort of why is it growing and then decreasing? Well, simply because by the end, right here, like all farmers already adopted, right? So there is an increase in adoption, and then you go through this peak when the particular year a lot of people switching to new corn, and then there is a decrease simply because you're running of new farmers, right? And eventually, when you're here, they all switch to a new corn. And if we look at cumulative curve instead of sort of this one, the cumulative curve, and we're going to see it on the next slide, will have this S shape, sort of classical S-shaped curve, where you got the moment of like saturation, and then so whether you get the moment of fast growth and then saturation. This is sort of the cumulative function, cumulative of this histogram. Now, one sort of key question was during this study was asked you guys heard about it, right? Why aren't you using it? And the answer was, well, because I look around at my neighbor farmers and they're not using it either. And so the point was that this innovation had a hard time to get started, and one of the reasons was really because of farmers not only looking at farmers magazines, but also looking at what their neighbors are doing, right? And then if you think about it, you instantly realize that, okay, well, there's probably some also network structure that can be used to understand and describe this process. So as I have said before, taking into this questions? Guys, any questions? Okay. So taking on this idea, and as I mentioned before, if you take that histogram and sort of integrate over it, where again the histogram telling us, how many farmers switch to this new corn, within the particular year, and if I take a cumulative function, which is okay, what's the total number of farmers that are using new corn? That's what we're going to get. This is the curve we're going to see. Notice it's sort of, the first growth, increasing, and then it saturates when you just literally run out of farmers and everybody using this. And it's kind of interesting how it's also the similar curves happens through different states, just with some delay, right? Now, can we actually come up with a model that describes this curve? Yes, of course we can, and it's a very simple model. This model was first introduced in 1960s, and it's called actually diffusion of innovation model, right? It's kind of described by Everett Rogers, and if you're actually interested in this topic, recommend. Though the book is old now, but it's kind of that's how things started. Okay, the question is, does it mean that started in Iowa? That's also could be the case, but Iowa, in some sense, it's the farmland of the United States, right? And so most of the farmers are there. So, and all like farming related events happening there. So in this sense, it's not surprising that Iowa was the first one who got sort of taken over. But you're right that it started with Iowa, and then it spread it around. Now, touching a little bit on this sort of marketing side of the things, I'm sure you have seen this type of curves that says, okay, when you have an innovation and you have like, innovators, early adopters, early majority, late majority, and then laggards in terms of like how you're using technology and switching to new technology. And, aggregated curve, if you just sum these things up, then you will get this, this yellow-orange curve, the S curve of like market share. So I promised you that there is a model that describes it, and there is actually a very simple model that describes it. This model is somewhat in the same spirit as the models we looked at on the previous lecture. Sort of, it's all, we can also write a differential equations that describe the process. And the equation is very, very simple. We'll go over it quickly right now. So imagine that we want to introduce a new product to the market, and we want to understand the growth of the product. So we'll define f of t is a fraction of people or agents who adopted this new product by time t, right? And fraction, just percentile from the total population. So to make this model interesting, we're gonna think about two types of agents, or two types of people, two types of consumers. One type is those spontaneous adopters, or those who just adopt on their own, and we'll call it coefficient. We'll call the coefficient P, and this coefficient will tell us sort of the intensity for those adopters. And the second coefficient will also introduce slightly different people and slightly different process, those who imitate, right? And there's an imitation process. So we'll have two processes happening at the same time. One is people just on their own decides to adopt a new product, maybe by looking at TV ads or something. And the other is imitators, those who actually see other people using the product and starting using the product themselves. All right, so that's sort of two different approaches. The same person actually, in fact, within this model can have like both, both sort of both levers, because this model is not about a particular person. This model about the fraction of a population, right? So it's population scale model. So the idea is the following: the fraction of agents that adopted at time t plus 1, it's those people who adopted at time t, plus so whoever else is adopted in this interval delta t. And who would that be? Well, it will be, first of all, 1 minus f is those people who has not adopted yet at all, right? So if f of t is a fraction who adopted, 1 minus f is a fraction who didn't adopt. And times p, it's spontaneous adoption rate. So we just take the population saying, okay, well, there is a 30% chance that they're going to just spontaneously adopt this innovation. Plus, those who are actually imitate, like copycatting. So again, this is a number of people who did not adopt, who are available to imitate. But imitation, they have to imitate from somebody. So this is a fraction or number of people who they imitate from. And this is a coefficient, the rate of imitation. So again, you can think about it as like, this person, looks at this type of people and with, rate Q imitates them. And so these are the two processes. And if I want to know the change of the fraction of the people as a function of time, I just, add up those two processes. This process, the process of spontaneous adoption, and the process of copycatting or imitation. And putting them together will give me a differential equation. I'm not gonna show you how to solve it, but it's actually very easy to solve this equation. And as a solution, you'll get this, S curve, and it's called Bass innovation diffusion model. And as a result, it gives you this S curve, where it tells you, the fraction of adopters, as a function of time. And I just put some parameters, and that's why it says, years. But the idea is always the same, right? So based on those parameters P and Q, this curve will have different shape and slope, but overall it remains this S curve. And of course, it reminds you, the curves we see for Iowa, for example. So that is, in bulk, the model of diffusion of innovation as it was seen in 60s, 70s, 80s, and 90s before the network theory. So that was sort of the state of the art back then. And it produces nice S curves. But if we want to go deeper and understand the mechanics of and mechanism of how this innovation propagates and spreads on the level of like individuals with their contacts and friendships, then we need to switch to a little bit different approach. We need to switch this network theory. But of course, for the network theory, you can look at the microscopic processes, but then you can sort of aggregate what's happening there and see the macroscopic behavior. And in fact, those microscopic processes sometimes causes very unusual patterns in a bigger picture. So before we switch to the network story, any questions here? No questions. Okay. But I cannot hear you by some reason. Can you guys say something? Okay, all right. Well, at least you can hear me. That's good. Okay. Why, or I'm sorry, I'm reading the question here. Why does the slope on the curve depends on P and Q? Yeah, because if you think about a little bit about calculus, the slope of the curve is derivative, right? And so if you differentiate this function, df, if you calculate df dt for this function, you do df dt, that will show you the slope, and the derivative will have these ratios, P and Q, right? You will know directly how it affects. Okay, so we're going to try to build this microscopic model of propagation of innovation within the network. And there are certain things, we need to make assumption about this innovation, right? There's certain things we need to know. So let's say we're trying to model of one technology taking over another technology. You can think about, I don't know, videotapes switching to DVD, or how now DVD is being phased out, and everything is happening online, or back in the days how fax were introduced. into the business world, and then how today they faded out. You know, 15 years ago, you would not see a single office without a fax machine, but today it's actually hard to find a fax machine in any office, right? So the technology completely was phased out by new technology, by sort of emailing, right? So that's kind of the technology propagation part. And the adoption of the new technology, of course, depends on a lot of variables, right? It depends on relative advantages. If like the new technology, the innovation gives you a lot of advantages in terms of business convenience, price. Then it's also the big question of how compatible it is with current ways of doing things. The complexity of the innovation, the possible to do trial testing, et cetera, et cetera, et cetera. But what's interesting is, to see this process, how new technology takes over, or how different technologies, if they can coexist at all. And like on example, when we're looking at the fact that we have, two dominating operating system, Mac and Windows, yes, two different technologies doing similar things can coexist, or we have like Android phones and we have iPhones. Again, two different technologies, but they do coexist. And so the question is, like, for example, what stops one technology from dominating and pushing the other technology out from the market? So to do this, to answer those questions, and actually, like see the process close, we're going to talk now about network structure. And the example I was trying to make is the following. When we thought about, say, news propagation, and we look at, say, this guy as a source of the news, a source of information, of course, the information will spread from him to his neighbors, and whether those guys want it or not, after some time, they will switch to, I'm sorry, after some time they will hear the news, or they will know whatever the W guys knows, or if the W has, I don't know, flu and you're in contact with him, they have a good chance of getting that flu. Now, it's a very different story if, for example, W wants, switch to a new, I don't know, got itself a new iPhone, or wants to go and participate in a political activity. And let's say there is this, he has the friend who is this, you guy, who has other sort of blue friends. Well, the you guy experienced influence from the red one, but also experienced influence from the blue. And if we assume that every person, for example, has a similar influence on this you actor, then obviously the influence from blue guys will be stronger, and the red guy will not be able to do anything. Well, and the same thing, for example, in here, even if you take this blue guy and there is one red guy, there's probably not that much chance that the blue guy even here will accept the change, right? Or will join W in protest. But if there is two guys here who want to do this, then there's a very interesting story becomes, because now there is two guys influencing him. Now the question will be like, what sort of the opinion of those two guys? So all of a sudden you realize that the network structure plays a role, because for the U, it doesn't matter how many reds are here, he still has only one connection to this red world, right? But for other guys here, the sort of influence can spread, right? And that's how network plays into this notion of propagation of innovation or influence. So in order to kind of formalize it, we'll look at the game theory approach, and we will consider this what's so-called network coordination game. Now, this is a very, very simple game where there are two players, and those players can play different strategies, okay? Now, depending on the strategy they play, they can have different payoffs. This is the language of game theory. Now, let me just speak it in like sort of plain English, right? Imagine that, you know, okay, you're using mobile operator, right? And let's say you're on MTS and somebody else on Beeline. Or you're on MTS and your friends want to to select an operator to go like also MTS or go Beeline. And within the system, of course, the phone calls from MTS to MTS person will be much cheaper than to call from MTS to Beeline, but the call from Beeline to Beeline person will be also cheap. So the question is, for this person who tries to decide, whether to select MTS or Beeline, what to do. Now, if those two people are sort of friends, and they do talk a lot. Let's say there's one person and another person, and they do talk a lot, and they each has to select like MTS versus Beeline. Then what makes sense for them is to coordinate their selection, coordinate their choice, right? If both select MTS, they get discounts from MTS. If both select Beeline, they get both discounts from Beeline. Now, just if we look at those two guys, then the problem will be answered quickly, right? It's just what's cheaper, both of them talk on MTS or both of them talk on Beeline. But the interesting part becomes when you realize that, each of them also have other friends, right? And by, just sort of selecting optimal connection here, right? It's not necessarily optimal for a bigger picture. And then you realize the friends has also friends, etc., etc., etc. So, it's actually becomes convoluted process to find like total optimum. And on top of that, of course, each person makes decision on his own without knowing like sort of the big picture. So, and the game theory helps us to sort of organize these thoughts and helps us kind of move forward with theory based on those ideas. So very, very simple right now. So two agents, A and B, and strategies, and strategies, strategies A and B meaning, going for two agents, and the strategies going for either Beeline or MTS, right? And if they both adopt the similar behavior A, I'm sorry, actually, in this picture, I called U and V players, and here it is V and W, okay? So let's call it U and V are players, and the strategies they're playing A and B. And if both of them select the same strategy, say go with MTS, they get particular payoff, right? So they get some sort of discount, right? If they go with strategy B, let's say going to Beeline, they get a particular payoff, another discount. But if they select opposite strategies, so one decides MTS, another Beeline, well, whenever they call each other, there is no discount, and so their payoff is zero, right? It doesn't matter who selects which one. And so this is what's called local network coordination game, right? It's local because it's between two players, and it's coordination because they win if they coordinate their action, right? So looking at this simplistic game, what should the strategy be for a person who tries to decide what to do, right? Well, the strategy is sort of obvious. Let's say this is the person who wants to make a decision, and there are a bunch of friends he talks to who uses one strategy B, and another group that uses strategy A, right? Your MTS friends versus your Beeline friends. If the discounts are equal, that you're getting from both MTS and Beeline, then the answer is trivial, right? So what would the answer be? What's sort of how the decision should be made? If both Beeline and MTS gives you equal, yeah, it's number of people, right? So if you have more friends on the Beeline, you go join Beeline. If you have more friends on MTS, you go join MTS. Now, if the discounts are different, and let's say we have like right here A and B, like two different levels of discounts, then the proportion of your friends that needed to be on like one side of the game or another, right, on the Beeline MTS, has to correspond, of course, to the discount that operator gives. In this sense, it's a very simple formula that, let's say, if A is the size of the discount, P of portion of people, of your friends that of that type, and times D, a total number of friends you have, right? If I want to switch to strategy A, well, what I need is for that A times B times D be greater than how much benefit you're getting from switching to B times the number of friends, proportion of friends you have in B times the total number of friends. So this is total friends you have in B. And that dictates a threshold. So here, for example, it's a threshold for switching from one strategy to another based on the number of friends. So you can accept new behavior when the fraction of friends, except that when the fraction of friends will be greater than this threshold. Now, if you look at this formula right now, if A is equal to B, then the level of threshold is 1/2, which is sort of obvious result that we know, right? If the advantages or bonuses you're getting from operators are equal, then it's just pure number of friends that uses that will will help you decide which operator to join. But if the benefits are slightly different, then the threshold can be not 1/2, but it will be, it will depend on the relative scale of those discounts you're going to get. Does this make sense? Okay. So because of those thresholds, we're gonna see or not see cascades in the network. And cascade is a sequence of the changes of behavior, or like chain reaction. So let's look at this network. Very simple network. And let's assume that and this network, let's say it uses particular technology or uses particular operator. And all of a sudden, we get two people here, the seeds right here, V and W, who changes their behavior by whatever reason. They got paid off by MTS to switch to MTS, or they bought, they got free phones or something. By their internal reasons, they switch to MTS. Now, let's say there is this threshold, and the benefits you're getting from joining one network is 3, another network is 2, and so this threshold is 2/5. So in order to switch, you need 2/5 of your friends to be using new technology. So what's interesting is if we pick up right now and look at, say, the node S. For the node S, it's actually 1/3 of the node friends using new technology. So it's only W. So node S doesn't have any incentive to switch. So node S is not happening here. But for the node R here, it's actually 2/3 of his friends using new technology already. So it's greater than 2/5, the threshold for the R to switch, and so it's actually going to switch. And the same thing with T. It's going to switch. So now the situation becomes slightly different. Now you have those guys switch to new technology. Now we can come back to S and reevaluate. And now S has 2/3 of his friends on the new technology. Well, 2/3 is greater than 2/5. So now S will switch. And of course, you will switch. And eventually, this new technology will take over the entire new network. Now, it wouldn't happen if we just had, say, one node with a new technology, because then for each and every node of the neighbors, the threshold for them will be like 1/3, which is less than threshold. They will not switch. But if initially two guys get in here, then the switching propagate. And you can think again about this, about the technology. You can think about political protests when you have, one person starting or like 2 or 3 friends starting. So that's how it spreads around. And that's called cascade, chain reaction. So sequence of changes of behaviors of nodes or actors. Now, I think this is actually the key concept here. Do you guys have questions? Is it clear why, at first it didn't switch, but they can eventually switch? So no questions. Okay. All right, let's see. Oh, I see there were some questions on chat. Yeah, well, pay several popular TV persons and the country changes opinion. Well, in some sense, yes. Now, what we just saw was this little cascade that completely changed, the opinion of 5 people. But as we noticed at the very beginning when we just start talking about this subject, the structure actually dictates how far this cascade can propagate. And I'm giving you an example. If we working still with the same, with the same, 3 and 2 sort of bonus levels, right? And their threshold is 2/5. And let's say, we have those 2 guys who are starting the story. Well, if we look at this, we realize that for guy number 5, again, it is 2/3 of his friends are switching, and so he will switch. For number 4, he will after that switch. Number 10 will switch. Number 9 switch, and even number 6 will switch. But now look what happens to the number 2. Number 2 is here connected through this lonely bridge, and so for number 2, there is only 1 out of 3 of his friends uses this technology, so 1/3 is below the threshold, so it's not going to switch. But it's also true for node number 12, for example, because here 1, 2, 3, 4 of his friends still using old technology, and only 1 are using new technology. So this is 1/5, again below 2/3. So all of a sudden, the influence will not spread. It will get stuck. It will spread up to here, and then no more. So this kind of result, you will never get in any previous BUS model or any other models. This result requires us to look at the substrate, looks at the network. And what you see, there are, for the cascade to stop, there are sort of 2 things that could happen. One is that you have like bridges connecting you to other groups of people. And, since it's a single bridge, the influence will not be able to cross it. Or the other groups of people are very well connected among themselves, and again, the influence cannot penetrate. And that's, by the way, a very good point why, like religious group is very hard to convince in the opposite opinion, or why there is like tightly groups of people. It's very hard to like break in and like for them to get into innovation or do anything else, because they're not listening to outside world, right? They're kind of reinforcing each other opinions, and innovation cannot spread into this. So in fact, those clusters and bridges are two barriers on the way of innovation. And you can sort of, I'm sure you have seen this in real life. Okay, but that's sort of the theory. The question is, with this type of theory, what can we do in practice? Oh, and by the way, I just, that's what I just described for this slide. I just jumped forward, but this slide shows you, yes, there are groups of tightly connected nodes, and the sort of lonely bridges. That's our barriers for innovation. This was sort of nice hand waving kind of model. We can formalize it a little bit better, and there is what's called linear threshold model that takes care of it. So the idea is the following: that it's now we're kind of trying to get to the modeling stage, and the same type of modeling. So the same type of modeling as we did for virus propagation, right? So we can assume that initially influence comes from some particular number of nodes, initial nodes, and the influence propagates along the edges. And for a node to switch, the fraction has to be, above a certain threshold. And for this model, for this particular model, we actually select thresholds for people randomly. Now, if you know thresholds for every person, you can actually assign it. Or you can just randomly, take a normal distribution. Say there are some people who has a very high threshold, and those who have very low threshold. One requires like half of the city to go on the demonstration to join the meeting, and for others, it's enough that 2 people are on the street, they'll be on the street. So then you have an initial set of active nodes, and then you iterate proactively through time and see how it propagates, right? And the person will get converted if neighbors, if there is enough neighbors, sort of the right fraction of neighbors, if the right fraction of neighbors will be around him. So let's see how it propagates. Here's a couple examples. This is sort of random network. And if you notice, in this particular case, the network, in the case A, the network was split into pieces, right? There's weak connection here. Guys, sorry, 1 second. Okay, so the network has those connections, and if you the red dots are initial seed nodes, and then we see how influence propagates. And depending on the positioning of the seed nodes as a function of time, this infection or influence can spread around.
So, Leonid Zhukov, could you mute other participants that we have here?
You do? Okay.
So we have some guy who haven't turned off
okay.
his audio. Thanks.
Okay, can you guys still hear me?
Yeah.
Okay. Okay, so and on this one you see initial. So you have a network, and there are some initial seeds, those red nodes, seeds of innovation or seeds of influence, and then how this influence propagates through. And you notice on the first picture, it, for example, propagates really fast on the top side of the graph, but slower on the bottom, but eventually spreads around. In the case B, it just doesn't propagate at all. on the case C, it propagates and covers the entire network. And so those networks and the propagation factors depends on the network structure. So the model we just saw allows us to formulate a precise mathematical question, which is called influence maximization problem. So what we want to do is select in the network a set of active nodes A, and let's say we know that the active set we can have to be 10 people or 20 people, some fixed number of people, and we can run a cascade from that set, from that initial set. Like right here, we have a cascade. We selected those two guys and ran a cascade. When we ran a cascade, it propagated up to here, but not further. And so from two initial nodes, we actually were able to create the cascade of size 1, 2, 3, 4, 5, 6, 7, right? So from two starting nodes, we actually created 7 people that switched to that technology. So 7 is called a cascade size, so expected number of active nodes when propagation stops. A0 is initial side of cascade. And so the question we can ask is to find the maximum optimal nodes that will create the biggest cascade. So let's say if we say, I can have only 2 initial nodes, which out of the nodes in this network we should, we should have we should seed, right, to maximize the cascade. I didn't do it on this network, but maybe, if you take these 2 guys as initials instead of 7 and 8, the size of cascade could be bigger, right? So you need to go through all the possible combinations to find the optimal combination, right? And, overall, this is what's called integer programming problem. It's a hard problem. It's computationally very hard problem, and, honestly unsolvable for very large networks. But there exists good approximation to those solutions. It's called greedy optimization, and I'm gonna just give you an algorithm how to do it easily and get within 70% of accuracy of the real algorithm. So here is the idea, and it's called the greedy maximization. It's greedy maximization because it's not going on and selecting and checking all the possible combinations, but it does it in a greedy fashion, which means, again, not going through each of them, but just incrementally improving, well, with the hope that we'll get to good solution. So first what we do is we select an initial node. Again, remember, we have all those nodes in the network. And let's say the goal is to select, let's say select 3 nodes that will maximize the influence. So in this sense, it's 3 nodes that will give us the biggest influence possible, all right? So the way to do this is the following. We select 1 node that we believe maximizes the influence. How we do it? Well, we go through all the nodes, select this node as a node, that we want, see how far influence propagates. It didn't propagate too far, fine. We deselect this node. Oops, it erased the whole thing. Okay. Let me recover it. Now it doesn't want to write. Okay. So I shouldn't be writing. So we select this node, for example, and calculate how far it's going to go, or we select this node, see how far the influence go, select this node, and let's say, we checked on the nodes, we went through all of them and realized that, as a single node, as a single node, this one gives the maximum influence. We keep it. We fix it. Then we take and start checking the following. If we fix this node and check this node and check this node and add this node or add this node or add this node, how far the influence would go from those two nodes. Let's say, we notice that if I select this red node and this red node, I'll get the largest possible influence from those out of all pairs of nodes. I fix those two nodes. And then I go search for the third node that will, together with these guys, give us the maximum influence. And you just do this until let's say until you get all your three nodes, the one you wanted. Okay? Not necessarily. It really depends. I mean, the question is, will the node with a maximum number of connections will be the first node? Not necessarily, because it really, remember, this is an influence propagation. And so if I have a node and it has a lot of connections, but all nodes it is connected to also have a lot of connections. That means if this node wants to switch, the effect, the influence from that node, from the central node on, let's say, this neighbor will not be that large, because this guy has, four neighbors, and so the value of the influence will be 1/5, right? So this is just only 1 out of 5 neighbors. Versus a situation when, for example, you might have a node with a low degree, but it's also connected to the nodes with a low degree. And then, for if this node goes red, for this neighbor, it's only one node, so there's complete influence. For this neighbor, it's 1/2 of his neighbors, so there is, still strong influence. So to answer your question, no, not necessarily. And that's why this is a computational problem. So it's very hard to just guess, which are the right nodes. But you use this algorithm, you go through it, it actually finds the right answer. And in fact, this is a very, very practical problem, because if you think about it, let's say you have telecom operators who tries to do marketing, right, and switch a lot of people, again, like MTS want to get people from Beeline, or other way around, and they can give away certain number of phones and do some freebies and switch people, right? They can decide who will get the freebies, so the person will switch. So this algorithm allows you to select the right set of people who will have the largest influence within the network. And so it would make sense to spend marketing budget to influence these people, to make them switch, and then they'll influence their friends. And the key message, I guess, from today's lecture is this influence is different from news or virus propagation, because in that case, how many friends your friends have didn't matter, because it was actually in the case of virus, you would want to address the person with the largest number of friends. But in the case of influence, not necessarily, because what you really need is the people who can influence other people. And so for other people who they will influence, they should be strong influencer, which means that other people should not be very much connected to somebody else, so these guys can influence it. Does this make sense? Somewhat?
Yeah.
Okay. And so this is not a very straightforward problem, how to select those maximum influence people, especially if you want to build a team. I mean, ultimately what you're trying to do is build a team within the social network that will spread the influence far away. And a lot of computational experiments show that quite often you want some people scattered, but you also want to have a core, people that connected to each other, and they can sort of propagate the influence from that core. So there had been quite a few experimental studies on that. And if you can imagine, especially talking about political unrest and social networks, this very direct application to modeling of uprisals and revolutions. And this is just an example. This is a slide of an example. It just tells you, experimentally, if you try to say this is a on the x-axis here, it's a model. On the x-axis, we're just telling how many nodes you target as you activate at the beginning, and the y-axis tells you the side of the cascade or the effect of those nodes. So if you select those nodes like randomly, right? Honestly, this is the side of the cascade you're going to get. This is like the largest side. You select 30 nodes, you probably get cascade, side of cascade, well, what is around 100. But if you select them according to the model in a smart way, then this will be the size of your cascade. And so 30 original nodes will create cascade, in this case, 40 times larger, affecting 1,200 people. Now, again, this is a model in a particular graph, but that gives you sort of the power, the idea of the power of the right algorithm applied to a particular model. And I think we're done with this lecture. As you remember, we started. I started by talking about this BUS model and Ryan Gross study done in 1940s. That's when for the first time people start talking about sort of separation of information propagation and actual influence decision making. And then there were papers in the 70s investigating and creating this BUS model. But in reality, like deep study of this phenomenon on the network started only around 2000. And so if you notice, most of the papers that I recommend you to read is 2000. And I guess the key paper here is this one by Kleinberg, maximizing the spread of influence in a social network. Okay, questions? Let me check chat one more time because I see there's been more things happening. Okay, all right. Okay, well then we're done. Ilya Andreevich, you there?
Yes, so we'll start, I can see the classes right now. We'll have very, very, very short break. And after that, we'll have 2 simulations, how to do this in R. Or what was the lectures, we'll see the implementation in R. So stay tuned, I will change Zoom IP in 2 minutes. Thanks.
All right, guys. Have a good one. Thank you. Bye-bye.
Bye.